Right. So Control L. Yes. Right. So right. Last lesson we were talking about the idea of the OSI model. We explained each and every layer of the OSI model. We saw that we have 7 different layers, and each layer sort of feeds into the next layer, so that it will allow and facilitate communication um, uh, across different systems. We said that essentially each layer communicates with the next layer via the use of protocols. All right, um, um, so that it makes better. It is implemented in such a way, all right, that no matter um, um, what kind of um, um, system or what kind of hardware you have in place, as long as the protocols are being followed, then you would be able to have this communication in place. All right. We said that the layers were the application layer, the presentation layer, session layer, transport layer, network layer, data link layer, and physical layer. And we've seen how they operate overall. In general, where do you actually see these layers operate? Well, in reality, if we take a look at the application layer, presentation, and session layer, those tend to work in terms of the file system driver. So essentially, they are operated, all right, by the drivers that drive the file systems themselves. All right, the transport layer and the network layer tend to make use of operating system drivers. All right, and the data link layer works on the level of your NIC card or your network interface card, whereas your physical layer literally works in terms of your connections, all right, and your different types of connectors, as well as your network card. Okay. Um, uh, Let me just update my attendance yet again, just to make sure everybody is here. Okay. So, um, uh, so if we had to take a look at these layers, we can sort of attribute certain protocols to each layer. So the application layer would tend to work with protocols such as HTTP, FTP, SMTP, DNS, and so on and so forth. So HTTP is for websites, FTP is for a file transfer protocol, SMTP is simple mail transfer protocol, DNS is dynamic name server, and so on and so forth. The presentation layer tends to work with file formats. So over here, we're talking about what type of files we're actually working with. So if we're talking about video, we're talking about WMV, AVI, MPEG, and so on and so forth. If we're talking about images, we're talking about JPEG, PNG, TIFF, what have you. Audio, obviously, WAV, WMA, MP3, and so on and so forth. The session layer essentially works with elements such as SQL, RPC, NetBIOS names, and so on and so forth. Transport layer typically works with TCP and UTP. More on that later. All right. Network layer tends to work on the IP or the IPX protocols. All right. Data link layer tends to work with Ethernet and HDLC, frame relays, and so on and so forth. And the physical layer actually works with the physical hardware that you're using for communication. I would like to point out that if you'd like to have another sort of like take an explanation of this OSI model, maybe in a slightly different way, I would highly suggest that you make use of this link over here. It actually explains the OSI model in a lot more detail, all right, in order to help you understand a little bit better how it works and what goes on, okay? So I would highly recommend the use of that link. So we talked about the OSI model. Now let's take a look at the TCP IP model. As we said, the TCP IP model is a sort of like simplified version of the OSI model. In fact, the application layer of the TCP IP model tends to sort of like group together the application, presentation, and session layer of the OSI model. The network interface layer of the TCP/IP model tends to group together the data link and the physical layer, and the network layer that is named within the OSI model is now renamed as being the internet layer or the IP layer of the TCP/IP model. All right, let's take a closer look as to what each layer is responsible for. All right, and have a better understanding of what the TCP/IP model is all about. So, starting off from the network access layer, so the most basic layer. All right, this layer is essentially the interface that you're going to have with the physical network. All right, essentially, as we said, it combines the data link and the physical layer of the OSI model. All right, and this is essentially the layer that is responsible of making sure that packets are moved, all right, on from um, moved on to the internet layer, so the layer above it once it receives certain packets, all right, from external hosts, all right. The internet layer, on the other hand, as I said, is the internet protocol layer. Essentially, what it does is defines the way, um, um, or a format, if you will, of how the data um, is um, is going to be delivered to the destination host. Okay. Um, uh, Essentially, what it provides is um, uh, it provides a form of routing mechanism that is going to ensure that the packets which would have a destination IP address will find their way eventually to their intended receiver. All right. Now, the IP address that you have on your computer is what is known as a logical address. It is not the real address of your computer, so much so that if you unplug a computer and plug it into a different network, you might be given a completely different IP address for that particular network. Essentially, every computer has what is known as a physical address, all right? And what this internet layer does is that it maps, all right, the IP address, all right, that you have, so the logical address, with the physical address itself. All right. The internet layer implements what is known as the ICMP protocol, or the Internet Control Message Protocol, which allows also for exchanging of control messages. All right. Such as, yes, I've received this packet, please send the next one. Error notifications, I haven't received all the packets, please send the missing packets, as well as other diagnostic tools that are used in order to message between different devices on the network. All right. In fact, this layer is one of the core um, elements or the core layers of the TCP/IP model, as it implements the IP suite. All right. Now, the IP suite, or rather the internet layer, is also a feeder into the transport layer, just like with the OSI model. The transport layer's responsibility is to enable end-to-end message transfer capabilities. All right. Um, so such that they would work along with segmentation, flow control, um, forwarding data to the right application via port numbers, and so on and so forth. All right. What do we mean by this? All right. Um, so essentially, the transport layer is going to be what is going to really enable the communication between two different hosts. Essentially, it is sometimes also known as the host to host layer. Um, this um, uh, this layer essentially identifies the way that these two hosts are actually going to communicate with each other. In fact, they they're usually split into two different protocols. You have what is known as the TCP connection and what is known as the UDP connection. The TCP connection is essentially a connection which is incredibly reliable. Essentially, whenever you create a TCP connection, all right, you are going to be able to acknowledge, all right, and trace and track, all right, that each and every packet that was sent is actually received, all right. So if you didn't get a packet, all right, that you were supposed to receive within a particular transmission, all right, the destination is going to know this and is actually going to send another request to the source host in order to resend that packet so that the entire message is actually received on the destination's side. All right. So essentially, as you can imagine, there is full error control within such a transmission. Okay. The UDP connection is unreliable in the sense that it does not wait around for missing packets, for example. It just receives packets and then deals with missing packets on the fly. All right. The the downside, all right, to the TCP connection, you might say, why not just always use the TCP connection and always ensure that the message is going to arrive um, uh, on the source destination, no matter what. Well, the downside with the TCP connection is that it is much slower. Imagine that um, uh, for every packet that you're receiving, you actually have to send an acknowledgement back, all right, to the source to tell them that you've really actually received that packet. All right. As you can imagine, the communication time is actually going to take much longer. UDP, on the other hand, is going to be much faster because you're going to be receiving packets, all right, for a specific duration, all right, and you're going to be the dealing with any missing packets on the fly, all right. A question that I would like, for example, to put forward to you is, in your experience, all right, what connections do you think make use of the TCP connection, and what other connections make use of the UDP connection? At least in what you would think. What services would you think make use of the TCP connection, and what services would make use of the UDP connection?
Streaming for UDP, probably.
All right, like
YouTube. Live.
live YouTube. Live
Ah,
YouTube, yes, yes.
Twitch.
In normal YouTube, that is TCP for the simple reason that it's already saved on a computer somewhere. Therefore, you don't need to stream.
And the packets, I'll make it there from start to finish, etc.
Exactly.
Alright.
In fact, you have an element of buffering if you think about it when it comes to YouTube, and sometimes it will literally stop, wait for the buffer to refill itself, and then you'd be able to continue with your playing. So yes, that would be a UDP connection if it were live. If it were not live, then it would be a TCP connection. All right. Any other examples?
A UDP connection.
Ping utility maybe uses UDP connection.
No, the ping utility uses a TCP connection. In fact, the ping utility would not work if you had a UDP connection, because if lost packets were lost, you wouldn't actually know that they were lost.
So it uses a TCP connection.
Yes.
All right.
Very much so. I don't know if any of you actually like playing games here.
Yeah.
If you play games online, all right, so multiplayer games tends to make use of a UDP connection. That's why, for example, you would have scenarios where you would see a character, for example, jitter around and swap from one place to another. All right, when they have quite high pings. All right, because essentially what's happening is that with a high ping, right, it means that packets are taking longer in order to actually arrive. And if a packet takes longer to arrive, then the chances of it actually being lost go up quite exponentially, and therefore you would start losing the quality of the feed essentially. Satellite transmissions use UDP, for example. That's another example. I don't know if you've ever viewed a video transmission sent by satellite, which was live, and sometimes you'd see the picture sort of like freeze, and then you have a sort of like pixelated version of that of what's going on. Yes, that would also be a UDP connection. Yes,
Can I ask something quickly?
yes, of course.
The trace route utility.
Hmm.
I think it can use both, no? Both TCP and UDP.
Yes, it can.
All right. Okay, because I wasn't sure, because I was finding a lot of examples on trace route across UDP, but not TCP somehow, and it kind of didn't make sense to me that it used only one.
I think it can be. It can use both. The problem, the reason why that probably it's used more with UDP because it's being able to find the fastest route from source to destination is more critical with UDP. If you know what I mean.
Okay. All right.
Okay. With
It's
TCP,
ideal for trace route.
as that. TCP, it's not really that much of an issue because eventually the packets are actually going to arrive. All right. And taking a look at Alex's contribution, yes, email uses TCP and voice calls like we're having currently. All right, those use UDP. So yes, you can have. So, for instance, if we take into consideration Discord, all right, the video stream that you're seeing, all right, both my share screen as well as the video coming from my camera and my voice, those are all using UDP connections and probably using different UDP connections. Whereas the text that you have within the text channel, for example, that is probably using a TCP connection, all right. So the same application could have multiple connections, if you will. All right, so it's not necessarily just a single connection. Okay.
Said.
Yes.
So essentially, a UDP connection is used by anything that is time sensitive. Is it correct to say that?
It's probably more going to be useful for a time-sensitive application. Yes.
Because I remember once we had discussed with regards to Apollo. I don't know if it was with you or not with regards to Apollo 16 when they had errors because it was time sensitive, but the
But
errors.
that was different. That was different. It wasn't because the data that was actually it wasn't actually being transmitted over a network, and the data wasn't actually arriving at the same at a time, um, by a specific amount of time. That wasn't the issue. The issue was that the CPU itself was receiving so many different requests at the same time that it was dropping certain unimportant instructions, essentially.
All right. Okay. All right.
That it was a bit different.
Sorry.
Excuse me.
Thank you for the clarification and sorry for mixing them up.
No, it's okay. You can have the thing is that you could have similar effects, really and truly. It could be a mixture of both in most scenarios. That was just because it was using a real-time operating system, which is different.
Okay.
All
Thank
right.
you.
Okay. Mala. Right. The application layer. The application layer is essentially the highest level of all of the protocols. It actually encompasses all of the interactions that it would actually be able to have with the applications themselves. So essentially, this is the level in which web browsers would be able to interact, all right, with the internet. So essentially, the application layer is going to provide that interface for the web browser. Same with email clients. Same with any other piece of software that um, makes use of the internet or networking capabilities for some reason. All right. In a very similar fashion to our OSI model, whenever you are sending data via the TCP IP system, all right, you are going to be sending your data and you're going to be feeding it through each and every layer. And each and every layer is going to, in turn, add its own header to the data that you're actually going to send. So, for example, if we have this data that we have over here, all right, once we send it to the transport layer, you're going to add to it either a UDP header or a TCP header, depending obviously on the type of connection that you're actually setting up. All right. Once you have that datagram completed, you would then feed it into the internet layer. Okay, which in turn would include an IP header over and above. All right, once that is completed, that frame data is then sent to the network access layer or the link layer, all right, as it's sometimes known, all right, where you add a frame header and a frame footer, thus creating the overall packet that is going to be sent along the network, essentially. Obviously, when it is received, on the other hand, all right, you would unpack the data, all right, in a very much reverse order to the way that it was actually constructed. Okay, in a very, very, very similar fashion. Okay. Any questions with regards to this?
Nope. Thank you.
Okay.
No, sir. Thank you.
All right. So when it comes to the TCP/IP functionality, all right, TCP/IP includes four very key design features which are very, 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 very important to the TCP/IP ideology. In fact, they constitute the whole point behind the reason why TCP/IP exists. These include the idea of logical addressing, all right, dynamic routing, name resolution, and application support. Let's try to understand what each area means. All right. Before we actually understand what logical addressing is, let's first take a look at physical addressing. So, physical addressing is essentially the address that is given to each hardware component that is going to access a network at some point. In fact, any device that has the capability of connecting to a network has what is known as a network adapter, a network card, all right, or network interface card, all right. And each one of these cards, all right, for every device that has ever been developed and known to man since the dawn of time, all right, has what is known as a media access control address, or what we tend to know as the MAC address, all right? It is unique for each and every device that has been created, all right? And it's usually created of 6 groups of 2 hexadecimal units, of digits, separated by colons or hyphens. All right, so this would be an example of a MAC address, and that would be unique to that network card, essentially. Okay, the first 3, all right, the first 3 sets, all right, those tend to identify the manufacturer. So, for example, in this case, 001CB3, that relates to Apple, whereas 004096, that relates to Cisco. And every other manufacturer would have their own version. Okay? The other set of 3, that would relate to the actual device itself, all right, that has been created. All right. Now, essentially, when it comes to routing packets on a network, technically speaking, we can make use of these physical addresses only. All right. Essentially, when data packets are placed onto the network, all right, the packet might have the originating MAC address of the originating NIC card, all right, and it will also have the MAC address of the NIC card where the destination needs to be set. Essentially, once the packet is placed onto the network, all right, the device will check to see whether or not that packet, all right, is 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 intended for that particular machine, all right, and it would read the packet, all right, that was intended for it, all right. Obviously, in normal circumstances, you would want that all other packets would be ignored, essentially. Okay. Now, the problem with this is that it's fine to do this sort of like procedure to check each and every packet that is coming in on the network. All right? It's fine to do that when you have a limited number of devices connected to each other. All right? But becomes very much impossible to do if we had to check each and every message that is on the network at any given point in time. Imagine, if you will, all right, that you are trying to see whether or not a packet is intended for your computer, and you're checking literally each and every packet that happens to be on the internet at any given point in time. All right, that's obviously going to be impossible, especially with the hundreds of millions, if not billions, of devices that are connected at any given point in time. All right, that is where logical addresses come in, come into to save the day, essentially. All right. What we do is we tend to to use logical addresses. All right. This is where the IP address comes in order to group devices on the same network. All right. Um, in such a way that their network addresses are related to one another. All right. The fact that they are related to one another means that the packets that are on that particular network, all right, are probably going to be communicating with devices on that same network. All right. Then what you would use is you'd have routed networks. So you'd have the idea of routers, which would be able to subdivide the network into smaller sub networks, also known as subnets. All right, so that it can automatically filter out which packets should be going to a particular subnet. So, for instance, if a particular packet, all right, has a destination IP, all right, with an IP address which has nothing to do with the subnet that we are currently in. It's not going to feed it in to that subnetwork. Therefore, what you're doing is you're reducing the amount of traffic and therefore the possibility of collisions that can happen on that smaller subnetwork. All right. Essentially, what you would do is you would read that the IP address for the packet that is coming into that particular network. If it is related to the subnetwork that that router is actually connected to, then it will feed it into the subnetwork. If not, it will pass it on to the next router in order to hopefully make that packet reach its destination a lot quicker. So as you can see, through the use of logical addresses, all right, we are reducing the amount of traffic, all right, within the subnets, all right, therefore making it a lot more efficient, all right, and a lot easier in order to have communication across various devices on the network. Okay, is this clear, guys?
Yes, from my end, yes.
Okay. So, so essentially, each and every computer, all right, on a particular network or subnetwork will have what is known as its own unique logical address. In any sense of the word, you would still need to have some form of address that is going to point to you. All right. Now, typically, the IP address can take of two different forms. You have IP version 4, excuse me, you have IP version 4 and you have IP version 6. IP version 4 is a 32-bit number, all right, which essentially um, allows us to represent our address, all right, using 4 numbers between 0 to 255, all right, for each number, essentially. And that is going to be what mirrors that particular device that is connected to a particular network to to the physical. It's actually mapping the logical and physical addresses together. All right. The IP version 4 is still in use, very much in use today. In the past, it was thought that IP version 4 wasn't actually going to suffice with the large explosion of number of devices that are connected to the internet at any given point in time. In which case, they have also developed the IP version 6, all right, which is very much similar in terms of notion, but it uses just more bits in order to create more addresses. Essentially, that is a 1 to 8 bit address versus a 32-bit address. Okay. So essentially, what the IP protocol or the Internet protocol would do is that it would route data packets between networks, all right, and then when a packet with an IP address which is related to the network that that particular router happens to be in, it will absorb it and um, uh, it would pass it on, all right, to the related machine with the related IP address. Okay. In fact, the protocol that is used in order um, uh, to match an IP address with a MAC address is known as the ARP protocol or the Address Resolution Protocol. And you also have the opposite protocol, which is known as the reverse ARP or RARP, all right, which essentially does the opposite, all right. It is what converts your MAC address back into the logical address, okay. This is just an example of what an IP version 4 address looks like, and this is what a similar IP version 6 address looks like. If you take a look at your own network adapters on your computers, you'd probably see that you actually have both installed on your machines. The reason is that if at one point in time IP version 4 is no longer suffices for the world's network needs, we will be able to switch over to IP version 6. However, they've been saying that we'll need to move on to IP version 6 for a good 20 years now. So we have actually prolonged the life of IP version 4 through the use of what is known as subnetting, which is something that we're going to be discussing probably not in today's lesson, but in our final lesson of the series, essentially. Okay. Right. So that is the first thing. So we had the idea of logical addressing. The second parameter that IP TCP/IP is built upon is the idea of dynamic routing. Essentially, a router, all right, on a network is a device which is going to read the IP addresses of any packets that comes its way. All right, its job is to determine where that packet should be routed to. That is why it's called a router. All right. In fact, usually routers tends to have a lot of outgoing connections as well as a lot of incoming connections. All right. Essentially, if you had to think about it, um, it's kind of like a junction, all right, in a traffic system, all right. Essentially, when a packet is sent, all right, the IP address is read, all right, and the destination of that packet, all right, is going to be forwarded depending upon what are known as routing tables. Essentially, you would have a table that is kept by the router, which is going to determine the best route, all right, that that packet should take in order to reach its destination. Okay, so essentially, you would forward it on, all right, to another router, all right, which will in turn try to see whether or not that packet should be connected to the subnetwork that that router is connected to, or it should be passed on to yet another router, and so on and so forth. The idea is so that eventually the packet will arrive at its destination at some point in time. Now, because a routed message could take various different routes in order to reach the same destination, all right, it could mean that certain packets would arrive out of sequence. If that is the case, then it is necessary for the host, all right, that is receiving these packets in order to reassemble them. In fact, the TCP/IP model also makes use of what is known as this dynamic routing or adaptive routing in order to solve the problem. Essentially, what we mean by adaptive routing or dynamic routing, we're saying that these routing tables will be updated automatically based upon information about certain routing protocols. All right, maybe packets weren't actually were not arriving at their destination. Maybe you were when you were sending certain packets, you were getting a lot of collisions along the way, and so on and so forth. Maybe a particular router that you used to send packets to is no longer online; it's now offline. These are all different scenarios that can happen on an active network. Therefore, you're able to update your routing table periodically, automatically, all right, then essentially you would be able to have a network that essentially would be working nearly autonomously, all right? So it is literally like a living thing, all right? So it is working in such a way that it seems you could essentially leave it as is and it will adapt to the situation accordingly. It's kind of like how a road network would tend to adapt as well to certain situations. So, for example, all right, if a particular route is blocked, all right, then more and more people on a road network would tend to start to find alternative routes. All right, that is what is known as an adaptive uh, routing as well, essentially, and something similar would actually happen with regards to routers. Okay, the third criteria upon which TCP/IP is actually based upon is the idea of name resolution. Now, what do we mean by this? It's all well and good being able to refer to a particular machine using its physical address, i.e., its MAC address. All right. It's also all well and good to refer to the same machine using its IP address, which is probably more user friendly than the MAC address. However, it is still not particularly useful, or it's still not particularly user friendly. All right. Um, uh, Essentially, what we can do with the TCP/IP protocol or the TCP/IP model is that we can, if we want to, give friendly names to certain IP addresses, okay, in order to help us remember um, the connection that we particularly desire. All right. Have you ever wondered how, for example, a a web browser can connect to a server from Google by literally typing in www.google.com? Google.com is much easier for us to remember than, say, something like 192.168.0.10, for example. All right. And I'm giving you a very basic and generic IP address because, people probably that particular www.google.com is much easier for us to remember than, say, a bunch of numbers. Take this in relation to every single website that you visit. It's probably easier to remember the website's name than it is to remember their IP address. Technically speaking, you can connect to these websites via the IP address. However, all right, it is not as user friendly for us. All right. The TCP/IP model makes use of what is known as a DNS service. Essentially, it allows us to store, all right, names of certain services. All right. DNS essentially means domain name service. All right. Where you'd be able to map, all right, the name of the service, such as google.com, with an IP address. Essentially, whenever you type in a name in the browser, in the browser tab, okay, what you are literally doing is you're telling the TCP/IP system to look through the DNS service and try to translate that domain name into an IP address via the use of lookup tables. If it doesn't actually find it, it will look for it in a different DNS server, and so on and so forth. If it doesn't find it at all, then you would say that that particular system doesn't exist. All right, so you might get a website does not exist. In fact, you would actually get a DNS error. All right, and that particular website doesn't exist. All right, so I don't know if I load up website such as, I don't know, jeremygrek.com. I'm sure that doesn't work. Here you go, because obviously it doesn't. So you get DNS probe finish, all right, DNS and NX domain. Essentially, what that means is it didn't find jeremygrek.com. All right, it doesn't exist. But that even if I do, whoops. So, jeremygrek.com doesn't actually work. There must be some guy on LinkedIn called Jeremy Grek, right, who works with Evolution Gaming. But anyway, that's a different story altogether. The point is, all right, that the DNS service doesn't actually have this this name in its lookup table, all right, and what TCP/IP actually offers is the ability to register, all right, domain names, all right, with certain IP addresses in order to make it easier um, for one to find. In fact, whenever you are buying a domain, all right, essentially what you're doing is you are buying um, a, a slot, all right, in this lookup table in order to make it easier, all right, for one to actually find your website, essentially. Okay. And finally, the last section that we're going to be talking about the pillars of TCP/IP is the idea of application support. As we sort of mentioned a bit earlier, all right, you might have several different applications running at the same time on your computer, and those applications might be making use of the network at the same time. All right, I sort of like alluded to it earlier with regards to Discord, for example. I said that you might have one stream for the share screen, one stream for the video, one stream for the audio, for example, and then another stream for the text. All right. But this is just one application. You might have other applications, like I just showed you. I had the web browser open. I might have had an email server or an email application running at the same time. I might have had a game running at the same time, and so on and so forth. TCP/IP provides a way, all right, in order to determine how a particular packet is related to a particular software application. How is it actually going to know whether a packet is reserved for this application or another application. Well, that is going to be denoted by what is known as a port. All right. So every form of communication, all right, from every application is going to be separated by a series of port numbers. All right. Um, so essentially, a specific port is going to be associated with a particular stream in order to identify that the data that is coming in via that port should go to a particular application. All right. Now, usually, whenever you see an IP address such as this, so notice this is a normal IP address. So you have 158.223.1.108. All right, that is an IP address followed by a colon 21. What does this mean? It means that we are communicating on this IP address over port 21. Okay, essentially, the packet, all right, is traveling to this destination, but is communicating on this particular port. Essentially, every application is going to create sockets, all right, which is basically a combination of the IP address and the port number upon which you're communicating. Okay. So essentially, this is sort of like the layer, all right, of application. An application would communicate over a particular port, either with TCP or UDP, depending obviously on the type of port that we're talking about. All right, that will then the the uh, the packet down to the network, out to the internet layer. All right, where you'd be able to map the MAC address, if you remember, with the logical IP address of the source and as well as the destination. All right, which in turn is fed down to the network access layer, which in turn is then fed on to the network. Okay. Any questions over here, guys?
The ports, I didn't understand properly. What's the use of the ports?
Mala. So essentially, ports are sort of like they are an indication as to what the data that is actually coming in is going to where that data that is coming in, whether or not it's actually going to a particular application or another. All right. So essentially, let's say, for instance, that I don't know, I am playing a game, all right, for example, and I want to know the positions of all of the other players who are playing the same game, all right, for example. That information might be coming into my computer, but at the same time, that might not be the only form of communication that I'm having on my computer at that particular point in time. Let's say, for instance, I'm also listening to some music via Spotify, for example. Okay. Then some other data is coming into my computer. All right. So imagine you have a number of packets coming into your computer. Some of them are going to be packets for my game, if you will, and some of them are going to be packets for Spotify. All right, for my audio. All right, and they're both coming in at the same time. How am I actually going to be able to differentiate the packet for for one application versus the packet for another application? That is where ports come in. So essentially, my game would say, "Listen, I am communicating." It will be sort of like coded into the system itself. We are communicating over this particular port. So I know automatically that if packets are coming in over that particular port. All right, let's say port 2000, for example. So port 2000 are going to be fed directly into my game. All right, whereas let's say Spotify is using port, I'm inventing here, all right, port 3000, for example. Okay, so the packets that are coming in on port 3000 are going to be fed directly into Spotify. So therefore, they would actually be able to route these packets internally, all right, in the computer itself, in order to arrive at the destination themselves. Now, ports don't necessarily have to be one way, all right. In fact, they're predominantly two way, as in you can communicate over the same port, all right, and send as well as receive data. Okay. I don't know if that actually answers your question.
It does. It's an identifier for the app, and it allows two-way traffic.
As
Essentially. Okay. Right.
exactly.
Okay.
What
Right.
is also worth mentioning, sorry, is that certain applications make use of certain what are known as well-known ports. In fact, the first 1024 ports from 0 to 1023, essentially. All right, those are what are known as well-known ports, which are used for specific types of communication. All right, so for example, if you are communicating for if you're looking for packets for web browsers, for example, you would use port 80 or port 31. All right, if you're using if you're using POP or SMTP or FTP, you'd be using different port numbers. In fact, there is a whole list, all right, which we can take a quick look at. All right, well-known ports. Okay, so here you go. This is quick Google. All right, so port 21
MTP.
is for file transfer protocol. All right, 22 is SSH, 23 Telnet, 25 SMTP, and so on and so forth. There are quite a few. All right, and you can also see them in terms of whether or not they're TCP, whether they're UDP, all right, and so on and so forth. All right, so 80 and 81, where are they? 80 is HTTP, all right, for example. HTTPS
443.
Yes, 443. All right, and so on and so forth. So you'd have the different protocols would sometimes be mapped to a particular port number. For anybody who has actually had to set up, for example, Microsoft Outlook with Google, you would probably have remembered that you had to play around with port mapping and port forwarding in order to be able to forward your emails onto your Outlook applications and so on and so forth. Essentially, you are making use of the well-known port that is used for email servers. All right, email services. Is that understood, guys?
Yes.
Yes.
Can I ask you
Yes.
something?
Yes,
So
of course.
these ports are physically hosted, let's say, in the firewall.
What do you mean?
Let's say these port numbers
Yes.
are physically hosted. Let's say the IT needs to open port number 43 to be able to do something, a new service, for example.
It's not. It's mana. They are enabled essentially through the firewall.
Okay.
Essentially, whenever you install a new application
Yeah.
that makes use of the internet, all right, and you're using it for the very first time. Usually, Windows brings up a window saying, "Are you going to allow an exception for the Windows firewall?" Usually,
Okay.
have you ever seen that?
No, to tell you the truth, I've never seen that, but we installed new systems and plugins, and they informed me that within your configuration you have to open port 5003 and 5007, for example.
For
And
example,
then
yes,
my IT said, okay, you have to open them in the firewall. So that is
yes.
why I'm asking you.
Yes. Essentially, that is essentially the same thing. But
Okay.
usually, if you install a particular application on your Windows machine,
Uh-huh.
and you run it for the very first time, it will say, "Would you like to include an exception within the firewall?"
Okay.
Essentially, what that means is, are you going to allow that port to be opened on the firewall in order to allow data to come through? If you
Okay.
don't do that, essentially you're going to stop your communication there and then. Essentially, your firewall is going to block any packets that are coming in.
Yes, in fact, that is what happened. And then when they physically went to it, they opened it. Okay.
Echo. You
It's like
open them.
it blocks the in and out.
Essentially, it's like opening. Imagine a port, all right, as being a border, all right. Whenever you
Yeah.
cross the
Okay.
border, I don't know if you've ever crossed the border, if you've ever been in a foreign country. Essentially, you're going to go through border control, all
Yeah.
right. If you have a valid passport, if you have uh, if you have valid credentials, you're going to be allowed through. If not, then they're going to detain you, or they're going to send you back, or whatever.
Okay.
Essentially, the idea is identical in a network. All right. Essentially, you are going to try to allow certain packets through a particular port. All right. If you have packets that are trying to infiltrate the system, um, via a port that is not open, then you're not going to be allowed in.
Yeah.
Essentially, all right.
Okay.
Now, doesn't mean that because you have um, uh, a particular port closed or a particular port open, then you're actually going to be secure. In reality, what can happen then is that people who are malicious will actually try to send you packets, all right, of data over a particular port which is open. All right. On the other hand,
Okay.
then you would have internal security systems that will double check it. All right. That's essentially the idea. Kind of like if you are if you're trying to enter a new country, if you have a passport, all right, that allows you to pass through that country, or rather pass through that border control check, they will allow you to get through. However, on the internal, all right, so in the country itself, you have a police force that would be enforcing any laws that you might break, essentially. So that would fall under obviously a different system altogether. Okay, that's
Thank you.
essentially the idea. All
Thanks a
right.
lot. Man. Thanks a lot.
Okay. So in reality, computers nowadays tend to use a hybrid between the OSI model and the TCP/IP model. All right. In fact, both models have their critics. All right. Essentially, it's kind of like Goldilocks, if you will. All right. Where the OSI model has too many layers. All right. Whereas the TCP/IP model has too few layers. All right. The hybrid model is one where it makes it has just enough layers. Essentially, what the hybrid model does is it combines the layers of the session and presentation into the application layer. All right. Um, for just like it does within the TCP/IP model, essentially. All right. However, the TCP/IP model has a problem where it doesn't differentiate between the data link and the physical layers. All right, in most textbooks, all right, for hybrid models, you would see that essentially you would have a very similar system to the TCP/IP model, where the network access layer is actually split into the data link and the physical layer, just like with the OSI model, essentially. Okay. I would highly suggest that you take a quick look at these resources, all right, in order to help you understand a little bit more what we have been talking about, all right. And that brings us an end to the idea of comparing the layered architectures that we started talking about. Right. Another thing that I wanted to mention was the standardization bodies that exist in order to allow all of these different companies to develop different devices that are able to communicate with each other. If you think about it, all right, it is very important for all of these different devices and different companies to be able to communicate with one another. And the way that they are allowed to communicate with one another is that each and every device and each and every company make sure to implement protocol standards. Now, somebody has to set the standard, all right? So if you set the standard, all right, upon which or upon the way certain devices are actually going to be communicating with each other, then you're going to be able to add different devices from different systems, from different manufacturers together, and they should still work well. All right. Essentially, when we're coming up with these protocols, we create layers of standards, all right, or protocol standards, which in turn determine how the data is going to be transmitted. So the syntax of how the data is going to be transmitted and how communication is actually going to be carried out. So communication rules. All right. And each protocol is going to add its own header to the data that is going to be sent, and in reverse, all right, each protocol is going to be able to extract the data, all right, or remove the header, all right, that was imposed upon sending when you're receiving, essentially. All right. So if you think about it with regards to the OSI model, all right, each layer is going to be adding its own header, all right, when you're sending. And when you're receiving, you are going to be disassembling the packet back down to the original data. If you think about it, the first three layers, all right, of the OSI model tend to manipulate or tends to work essentially on the data itself. All right. Then the transport layer thinks about how the data is actually going to be segmented. The network layer thinks about how it's going to be packaged. All right. The data link layer is going to create the data frame itself, and the physical layer is going to actually transmit the bits of information across a physical medium. All right. And obviously, that the reverse is done on the receiver's end, essentially. All right. Now, when we talk about standards, all right, we are talking about two different types of standards that are being implemented by different vendors in order for these products to work together. All right. We have standards which fall under the type de jure, all right, or by law, and you have standards that fall under the type de facto or by fact. De jure basically means that it is produced by a standardizing body, all right, and that produced and accepted by a standard by a recognized standardizing body, and is implemented in hardware and communications. De facto standards are standards that are gained through market forces, all right, that are sort of like enforced via certain software, which could also be proprietary or as well as open source. Okay, so essentially, de jure standards are standards that are sort of like set by the standardization bodies. De facto standards are ones that are sort of like imposed later on, all right, even by standard practices, all right. Sometimes it could be the fact that certain de facto standards would make their way into de jure standards, essentially. Okay, so when something gains widespread popularity, then it tends to move into a de jure implementation. De facto could be the lighting cable from Apple instead of Type C when talking about USB. Well, to a certain degree, yes, as in the different types of connections, for example, that are the different types of connections that are currently being touted. All right. For example, let's take a step back. All right. So the normal USB connection. All right. The normal USB connection was a connection that in turn was basically the universal, all right, in fact, hence the U in USB, all right, the universal connection that sort of made a series of different other types of connections obsolete, such as the PS2 connection, such as the serial connection, all right, and so on and so forth. I don't know if you've ever taken a look at a SCSI port, all right, or people older systems made use of various different types of connectors depending on um, the uh, the application or the hardware that it was actually connected to. However, the use of the USB port became so um, so important, or rather, it was becoming so popular that um, certain types of ports tended to sort of like phase out with time, right? And eventually, you get the USB as being the de facto port used pretty much for most devices that you're actually connect the devices. Nowadays, the shift is happening from USB, normal USB, to USB Type C because USB Type C is faster. USB Type C allows more data to pass through it. It can allow for fast charging. It can allow for video and so on and so forth. So even ports like HDMI and DisplayPort and all of those might actually be phased out with USB Type C. I am sure that with other types of connections, yes, you would have something similar. All right. Same thing happens over here with regards to standards that are implemented in networking and communication. Okay. Does that answer your question, Alex? Okay. So, what goes into the standardization process? So, first and foremost, you need to specify, all right, and identify what the problem area is. All right, so you're going to be specifying the area that you're going to be developing in and identifying what the problem is. Then you examine the various different alternatives of how one can actually achieve the same solution. However, in this case, since we're talking about communication, probably you're going for the most optimal. All right, so you look at the most optimal solution to solve that particular problem, and then what would happen is the area of acceptance, essentially where you define what the solution is, and then you enforce it in the industry so that it is recognized and implemented, essentially. Okay. So what we're going to do now is we're going to take a look at several different standardization bodies in order to have a better understanding of who these people are and what they actually do. So the first standardization body that we're going to be looking at is the ISO, all right, standardization body, which stands for International Organization for Standardization. It is essentially a group of other standardization bodies, all right, such as the ANSI, the BSI, and for AFNOR and DIN, all right, members, meaning American National Standards Institute, British Standard Institute, Association Française de Normalisation, and Deutsche Institute for normal, so essentially German Institute for Normalization, essentially. All right. These people set standards in many areas with regards to communications, and you usually be able to identify their standards by the ISO prefix. So you'd usually see something which looks like this. So ISO 4335, that is essentially means it is standard 4335 developed by this standardization body. We can take a look at their website, all right, in order to be able to have a better understanding of what they provide in terms of standards. All right. Another standardization body is the ITUT, all right, or the International Telecommunications Union of Telecommunications Standardization sector. All right. It is actually a part of the United Nations. All right, and it's comprised of governments and other regulatory agencies, as well as suppliers and network operators. All right, and they tend to prefix their standards through a letter of the alphabet before a specific number. So V.24 and X.25 and Q931. These are all different standards that have been implemented by the ITUT. All right. And yes.
Sorry, I just realized something. At one point during the lecture, you mentioned that we are going to look at some topics in the next lecture, right?
Yes.
Our exam is next week for this topic
No.
on the 24th. Sorry, Tam, I just clicked all of a sudden. Kont qed nara l-kalendarju.
No. Let me just. I was under the impression that we had another lesson.
We have, but it's for 10338. At least it's earmarked for computing architecture, not.
No. Let me just double check. Tom. Give me a moment.
Thank you. Sorry, Ta.
Anzi. I was under the impression that we had another one. Away. Back to internet. So this month today is the 14th. Mana. Aha. All right. That was the test. Yes, because it's on the 24th. You have the test, right?
Mhm.
Right. Okay. Okay. What I Mara. That is all right. That puts a bit of a spanner in the works. So, quick question: would you guys be available for an extra lesson this Friday?
Personally, I'm a bit tied up at the moment, to be honest, because
For me too, it would be tough this week.
All right.
given personally, given that I have 4 exams, or I have all the study sessions planned out as well, and it's
Hmm.
quite the 11th hour, to be honest.
Right. Okay. And Saturday morning would be outside of the question as well, I would imagine.
Definitely.
All right.
From my end, sorry.
Mana. So, right. Would it be okay for you if we actually went a little bit further today? Maybe stop at 8:30 rather than at 8.
Will, will we be able to cover the subsequent 4 chapters? Because
What
there's four topics
what
here.
I would do is I would go over the more important chapters. All right, the ones that I'm not literally going over the slides. Essentially, I'm actually explaining certain things. So, for example, these sets of slides, they're very easy for you to go over yourself because all that these slides are actually putting forward are the different types of standardization bodies that there are out there and their prefixes essentially.
Okay.
You know, to follow something like this, probably you'd be able to read on your own yourself. Yes. But then I will be able to go over the nitty gritty of other topics in a bit more detail, essentially.
Okay. All right.
All right. Is that okay with the rest of you guys?
It's okay, man.
Yeah, it's okay.
All right. So let's. So with regards to these set of slides, I would suggest that you would take a very quick look at them. Essentially, they go over the different types of standardization bodies that exist. All right. And what type of what they actually consist of, as well as their prefixes. All right, it's essentially going through all of the different sets of standardization bodies that have to do um, um, with regards to communications. All right, there wasn't actually much left in the slides for this set of slides anyway. All right, so that is that. All right. I would also suggest that you take a little bit of a look with regards to network devices. What I would mention, all right. So essentially, over here, what we're talking about within these set of slides is that when it comes to network devices, different devices tend to communicate over different layers within the OSI model that we were talking about. All right. Essentially, what I wanted to point out was that there are what are known as level 1 devices, level 2 devices, and level 3 devices. All right. You probably have heard of a number of different types of devices, such as the repeater, such as the hub, such as the router, the switch, the bridge. What are all of these? And sometimes they are actually used interchangeably. What I wanted to point out was that they do actually have a difference, okay, and they do actually operate on different levels. So first and foremost, we're going to be taking a look at the repeater. So the repeater is a simple device which takes a signal and repeats it at a higher intensity. It's usually used in terms of Wi-Fi signals in order to intensify the signal and broadcast it again, essentially. Okay. Essentially, by doing that, you are increasing the distance. However, it's also going to consume a little bit amount of time, therefore making any connection to a repeater slower. All right. Similarly, all right, you have what is known as a hub. A hub is essentially a wired version of a repeater. All right. Essentially, it receives a packet, all right, on the hub, and it copies that signal and repeats it, all right, over all of the ports, all right, all of the other ports in order to make sure that it goes to its destination. Obviously, by doing that, um, it um, uh, it is actually sending packets to destinations which don't necessarily need that data to actually be sent to it. All right, it can also cause a number of collisions, and it also can cause a number of jams, although you can have some collision detection features, all right, in certain hubs. These are some examples of these hubs that we are talking about. Now, the disadvantage of a hub is that there is no form of routing intelligence. All right, essentially, it is a device that increases network traffic because essentially we are literally propagating the same message over all of the other ports for every packet that comes in from the into the hub. All right, and it's also increasing the risk of collisions due to the high amount of traffic that is actually passing through these devices. All right, it's typically very similar to the idea of an internet chat room whereby you would have multiple people communicating in one single chat room. If you have 2 or 3 people within the single chat room, it becomes quite manageable. But the more people you start adding to that same chat room, the more unmanageable it becomes, and possibly it could actually slow down communication between all of the different people involved. These devices, both the repeaters and the hubs, are known as layer 1 devices, i.e., they work literally on the physical layer. So the repeater takes the signal and amplifies it, and the hub takes the packet that arrives and copies it and broadcasts it to the different levels. It doesn't need to unpack the packet any further than from the physical layer. All right. That is essentially what we know as a layer 1 device. A layer 2 device includes devices such as a bridge, all right, or a switch. Okay, a bridge is essentially a device that allows one to connect one or more LANs together. Essentially, they use the MAC addresses in order to be able to handle and filter traffic flow. All right. So essentially, a bridge will allow you to connect various different um, networks together. In this case, we have 3 networks connected via a simple bridge. A more advanced version of a bridge would be a switch, which has multiple ports. All right. Essentially, it allows easy connection of more networks. All right. And in fact, it can allow multiple computers to be connected with it. It's more flexible, all right, and it inspects the data and transmits it to the correct destination. So this is an example of a switch, on the other hand. However, both the bridges and switches, mainly switches, are layer 2 devices. Why are they layer 2 devices? Because they are interacting with the MAC address, all right, which is going to be read only within the data link layer. So essentially, every packet that comes in is unpacked, read in terms of the MAC address, and then forwarded to its destination, all right, based upon a MAC address table that it actually has populated inside of it. Okay, so that is a level or a layer 2 device. A router, on the other hand, is what is known as a layer 3 device. A layer 3 device, all right, such as the router, has a higher degree of intelligence as it is used to connect one network to another network. It actually allows 2 or more networks to be connected, either LANs or WANs, all right? In routers, essentially, what it does, it takes into consideration the IP addresses of those devices and plans them with respect to routing tables, all right? So it takes the incoming packet, inspects the IP address, figures out whether or not that IP address is within the network that it is connected to or is connected to another network, and passes it on if necessary. All right. But in this case, it is actually working on the third level. In this case, the network level. All right. So essentially, the source is sending a data packet, communicating over a physical layer. All right. It is read by a router. All right. And the packet is disassembled up to the network layer. The router via the network layer will identify whether or not it needs to pass it on to another router via a routing table, in which case it would recompass it and send it on its merry way to the next router, all right, based upon obviously its destination IP address, all right. The other router might disassemble it as well in order to identify the destination device, all right, via the IP routing table, and then send it to the destination like so. All right. So this is essentially the idea between um, a layer 1 and a layer 2 and a layer 3 device. Is that clear, guys?
Yep.
All right. Some more information and some more resources can actually be seen via this link over here. Okay. Right. So this set of slides over here basically is a set of slides that is going to be used in order to identify, all right, or to help you identify the different components that make up the TCP and the IP headers of a packet. All right. Essentially, whenever you are sending a TCP IP packet, all right, over the network, you are going to have both a TCP header as well as an IP header, and it's important for you to understand what are the components that make up these headers. Okay. So essentially, as we remember, all right, when we're talking about the TCP/IP model, all right, the application is talking with the transport layer, where the transport layer is going to apply the TCP or the UDP header, depending upon obviously the application protocols that we are using. Those in turn are fed into the IP, all right, the IP layer, all right, or the internet layer, all right, which in turn is going to apply the IP header, which in turn is going to feed it in to the network access layer in order to be able to send it across the network along its merry way. This here is what is known as the TCP IP header, or the TCP header. It has a source port and a destination port. So 16 bits are reserved for the source port, all right? And 16 bits are reserved for the destination port. You have a 32-bit number that identifies the sequence of this particular packet, all right? So the sequence number that is actually used for this particular packet. So essentially each and every packet has its own unique sequence number. Therefore, you would be able to know where this particular packet fits along the set of other packets that it has received. All right. You have the acknowledgement number, which is essentially the number that you are receiving in acknowledgement from the other from the destination computer, essentially showcasing whether or not this sequence number has actually been received. All right. So essentially, whenever you are receiving back this acknowledgement number with this acknowledgement flag back from a packet from the destination, essentially it means that this packet has actually arrived at its destination. All right. You have a certain number of bits reserved for your offset. You have a certain number of bits which are reserved. You have a certain number of bits which are used for flags. All right. So this is a single bit, single bit, single bit, single bit, single bit, and so on and so forth. You have 16 bits reserved for your window size, 16 bits reserved for your checksum, 16 bits reserved for your urgent pointer. You have a number of bytes reserved for your options, and which is variable, all right? And you have a number of bits used for padding, all right? Essentially, these are the details for it. So essentially the source port is the source port number. So destination port is the destination port number. Sequence number is the number of the first data octet or the data byte in that segment. Acknowledgement number, which is also 32-bit, is a number that if the acknowledgement flag is set, the field contains the value of the next segment that it is expecting. So essentially, if the acknowledgement flag is set, then the number that is being set within this acknowledgement number is the number of the segment that I'm expecting for the next data packet that I am going to receive. All right. The data offset is a number. All right, which is the number, or rather, of 32-bit words in the TCP/IP header. So essentially, is going to determine how long your header is actually going to be. All right, so it indicates essentially where the data is going to begin. The reserved number of bits is reserved for future use. All right, the window 16 bits is the number of bytes accepted from the start, from the one in the acknowledgement field. So starting from the one in the acknowledgement number over here. So essentially the number of bytes accepted from the value in the acknowledgement field. All right, and then you have your flag bits. So you have your sync flag, all right, which is going to be used in the three-way handshake, which we'll be discussing in a moment. We have the acknowledgement field, which is essentially a flag to set whether or not You have an acknowledgement, yes or no. The fin field, essentially, this is when you are finalizing, all right, or finishing a connection, all right. You have the push bit flag, which essentially is going to push the packet out, even if the packet is not full, all right. Because usually packets are actually sent when they actually fill up a particular amount of data and then they are sent. So sometimes you might want to send packets which are not entirely full, like you would send trucks out which are not entirely full. Okay, you have your reset flag, all right, which is a flag that is used for error checking. You have your urgent flag, which is used in order for high priority data, and you have your CWR, which is the congestion window reduced, and ECE, explicit congestion notification echo. These are essentially flags used for congestion mechanisms, essentially. All right. And then you have a number of other details, all right, such as the checksum, all right, which is used for error detection, the urgent pointer, which defines the points, which points essentially to the sequence number of the data packet, which is going to be urgent data, all right. The options set of bits, which is variable, which are going to be multiple of 8 bits, which essentially provide additional options such as um, um, maximum segment size, etc., etc., etc. You also have padding, padding set of bits, which is variable, which depends entirely upon, all right, the number of bits that have been used within your header. The idea behind the padding is so that your TCP IP header will always use up an integer amount of 32-bit pieces of information. So essentially, you wouldn't have um, sort of so as you can see, all of this data is stored within an integer number of 32-bit pieces of data. So you wouldn't have, the last piece of frame with some data, which is the data starting from over here. It's always going to start after an integer number of 32-bit 32-bit bytes, 32-bit words, all right, that make up essentially your TCP header. Okay. So that basically is your TCP header. In a very, very similar fashion, you have an IP header, all right, which again is 32 bits in length, all right, in terms of it's made up of 32-bit words essentially, all right. You have 4 bits reserved for the version that you're using, whether it's IP version 4 or IP version 6. All right, you have another 4 bits which determines the length of the header of the IP header. All right, you have type of service, which is 8 bits, which essentially determines the type of service that you're trying to implement, whether you're trying to minimize your delay, maximize throughput, maximize reliability, and so on and so forth. The total length, which is 16 bits, is the total length of the IP datagram in bytes. Identification, 16 bits, identifies the IP datagram, all right? You have 3 bits used for flags. 1 is reserved, 1 is used for don't fragment and one is for more fragmentation. Essentially, it is to not to fragment this particular datagram or to fragment it. You also have a fragment offset, which is 13 bits in length, all right, which contains the offset from the start of the IP datagram when the datagram is obviously fragmented. Okay. You have a time to live. All right. So this is something that we had discussed last lesson. All right, which is 8 bits, which is essentially a counter which decrements for each hop that IP packet makes on the network. You have a protocol which is 8 bits, which is used by the transport layer protocol, which is used in order um, to make the data in this datagram processed from the destination from the destination's point of view. All right, you have the checksum header, which essentially checks the integrity of the datagram. You have the source and destination IP addresses, which in turn are the 32-bit numbers that define the IP addresses of the source and the destination, as we had sort of mentioned earlier. All right. You also have some options, all right, within the IP header, which could be set. This can take up a variable number of bits, all right. And you also have a padding number of bits, which is also variable depending, obviously, on the type of the amount of options that might have been used in might have been used. So essentially, what you want to do is you want to make sure that the number of bits used within your IP header is also making use of a number of multiple 32-bit chunks of essentially. All right. Again, some more resources in order to help you understand this a little bit more for for you to understand essentially. Okay. Right. So this is one of the more important topics that I wanted to sort of mention for this course. All right. It is the idea of IP addresses and subnetting. All right. So essentially, as computer scientists, we should be able to understand a little bit more the idea, all right, behind IP addresses and what and how we can actually manipulate these IP addresses and how we and for us to be able to understand what certain IP addresses provide to us and what they allow us what they allow us to achieve. So first and foremost, it's important to note that when we're talking about the IP version 4 system, all right, we're talking about a 32-bit number, all right, which essentially gives us 2 to the power of 32 different numbers, which is around 4 billion different addresses. However, unfortunately, there are a number of these IP addresses which are wasted and or reserved for special implementations. So we need to be able to identify the types of IP addresses that we are actually working with. Okay, so one thing that IP addresses have is what is known as a class system. Essentially, uh, IP addresses fall under a number of different classes: A, Class B, Class C, Class D, and Class E. And the way that you're able to identify, all right, under which class a particular address falls under is through the identification, all right, of the first byte. If the first byte, all right, or the first number within the IP address, all right, falls between 1 and 126, then we know that that is a class a class A IP address. If the first number falls between 128 and 11 and 191, that is a class B IP address. If the first number falls between 192 and 223, that is a class C IP address. If the first byte falls between 224 and 239, that is a class D IP address. And if the first number is between 240 and 255, that is a class E IP address. In fact, what we call a class A system is, or a class A IP address. Usually, a class A IP addresses are reserved for large networks. Class B networks are reserved for medium networks. Class C networks are reserved for small networks. Class D are used for multicast networks, and Class E are used for experimental networks. Now, when it comes to Class A networks, all right, the number of networks or possible networks that we can actually have, all right, within the Class A IP address is 123 different networks. All right. However, that is because we only have one byte, all right, that is reserved essentially for the network ID. However, we have 3 bytes in order to identify the host ID. Essentially, a byte means 2 to the power of 24 different hosts. Why 3 bytes? Because 1 byte is 8 bits, all right? 2 bytes is 16 bits, 3 bytes is 24 bits. So 2 to the power of 24 is 16.7 million different hosts. That is why it is used for large networks. Class B, on the other hand, all right, has 2 bytes reserved for the network ID and 2 bytes reserved for the host ID. All right. However, all right, since you're not using the full range of the 2 bytes for your network ID, all right, you have slightly less network IDs than you have hosts. All right. Class C uses 3 bytes for the network ID, therefore giving you 200 and 2 million and something different networks that you can have. However, each of these networks can only support up to a maximum of 254 different hosts. This is important to realize, all right? So it is very, very important for you to be able to identify whether or not you're talking about a Class A, Class B, and Class C, Class D, or Class E, all right, IP address by looking at an IP address. Essentially, you would look at the first number. The first number happens to be between 1 and 26 in this case, therefore it is a Class A network, all right? But a Class A network, all right, since it uses 3 bytes in order to address, all right, its addressable spaces from 000, all right, in the next 3 bytes up to 255, 255, 255, all right. Notice, because we're talking about host bytes, all right. These 3 numbers over here represent 3 different bytes, all right. 0 is the smallest number for each byte. 255 is the maximum number for each byte. So essentially, all right, for a Class A network, all right, with network ID 10, all right, we can host a device devices from 000 up to 255.255.255, all right, over network ID 10. Class B, on the other hand, all right, these first 2 bytes define the network ID. However, these 2 bytes over here define the host ID. For class C, all right, the first 3 bytes define, all right, the network ID, and the last byte defines the host ID. Is this clear, guys? Because this is very important. So for class C, all right, typically, all right, or by default, all right, for class C, the last byte is going to be used in order to identify the host. Yes. That's a mistake. It's a mistake. This should be 0. All right. Sorry, this should be 0. Okay. All right. So essentially, the first 3 bytes are going to be what defines your network ID. The last byte defines your host ID. Okay. So essentially, whenever we're talking about, you might have come across the idea of subnet masks. Subnet masks are essentially masks that allow us to identify, all right, the the network that this particular class happens to be under. All right. So essentially, whenever we're talking about a class A network, all right, in order to be able to sort of like filter out the IP address, all right. No, let me just open up very quickly.
There.
Yes.
In our case, we always use Class C, I guess, when it comes to internet service and our
Not
internet service provider, I guess. Hey,
Not necessarily. No, you would probably use a Class C on your LAN. Your ISP probably uses a Class B.
Class B.
In smaller countries, in larger
Uh-huh.
countries, it might be a Class A.
Oh, all right, all right. So it depends on the exactly how you said, like
It depends on
the number.
on the implementation. All
Mm,
right, and you
all
could
right.
also then have, for example, in my home, I am using a particular set of IPs, all right, which are probably the same kind of IPs that you're using in your own home, all right. For example, if you're using a Class C network in your home, then you're going to be using a certain IP. You're going to be using probably the Class C IP addresses, probably. But even though I might have a similar IP address on my network as you might have on your network, it doesn't mean that our networks are then connected.
I see.
Because
All
we
right.
can, because then the IP address that I am obtaining from my internet service provider is going to actually be a Class B. This is why we are able to actually stretch the use of
IPv4.
of IPv4 essentially,
Mm-hmm.
because
All
we're
right.
reusing certain IP addresses
I see.
in certain circumstances, um, especially when it comes to local area networks.
All right. Okay.
Okay,
So it's not. I mean, it's not like it's always Class C. It can be different in
it can be
different
different. I mean,
households. Different.
you could set up your router to be a Class A router, but
I see.
the IP address that is actually coming in from your internet service provider is different.
It's different.
Because
Alright.
it
Okay.
depends entirely and then upon how many devices you're actually going to be connecting
Exactly. No, exactly.
in
Alright.
your network. All right. So, for
Alright.
example,
Okay.
at St. Martin's, for example, it wouldn't make sense to have a Class C
See.
IP address. It
Mhm.
actually has a Class A IP address because you have the amount of different devices that actually can be connected at the same time.
Exactly. Alright. Okay.
That's the idea.
Thank
Okay.
you.
Voilà. I was trying to explain this idea of the subnet mask. So let me take an example of an IP address. Okay. So I'm going to take this one. All right. This IP address 10.250.1.1. Essentially, underneath is going to be trans is going to be configured as a binary number such as this. So 10 is 1010. All right, in binary. But let me write this in 8-bit format. All right, so I am going to make sure that in terms of 8 bits, it's 0001010. All right, 250. All right, on the other hand, so 250. All right, is 11111010. All right, and the rest is actually going to be 7 zeros. So 4, 5, 6, 7, 1. And the last one is going to be identical. All right. So 1, 2, 3, 4, 5, 6, 7, 1. All right. This is our IP address in decimal format. And this is in binary format. All right. Now, our IP address, since this is a class A IP address, all right, that is going to have this subnet mask, which is 255.0.0.0, which in turn, all right, if we had to convert, all right, obviously this is in decimal. If I had to convert into binary, would be 1, 2, 3, 4, 5, 6, 7, 8 point 0, 0, 0, 0, 0, 0, 0, 0. So 1, 2, 3, 4. Yes. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4 in terms of binary. Do you agree with what I just did over here, guys?
Yes, so far so good.
Yes.
All right. So, what is a subnet mask? So, essentially, what is the point behind the subnet mask? So, the idea behind the subnet mask is to take your IP address and you AND it, all right, using the AND bitwise operator with your subnet mask. Okay? And the result should be your network ID. All right. What do we mean? What do we mean by this? So essentially, what we would do is we would line up these binary numbers. All right. Let me take the first byte. All right, if you will. All right. So our IP address. all right, for our first byte is 0, 0, 0, 0, 1, 0, 1, 0. And we AND that with 1, 1, 1, 1, 1, 1, 1, 1. All right? So 0 and 1 is going to give us 0. 1 and 1 is going to give us 1. All right? 0 and 1 is going to give us 0. 1 and 1 is going to give us 1. 0 and 1 is going to give us 0. So all of these over here are going to be 0. Do you understand what we've just done over here?
No.
Essentially, what we're doing is, remember, we talked about logical operators for those of you who and logic gates for those of you who did intermediate computer architecture. We said that with the AND gate, all right, we will get a 1, all right, if both inputs are 1. Take this as sort of like being our first input, and this as being our second input, all right? If one of our inputs happens to be 0, then the output is going to be 0. It doesn't matter which one it is, all right? In
Then-
this case,
Sorry, but then in this case, if we have a subnet mask that is all ones, essentially our network ID is only the IP address. No?
if it's all ones, but notice it's not all ones because this part is zeros. From here onwards, it's zeros, no?
So essentially the full.
I just didn't write the full 32 bits in my case, so forgive me. All right.
Okay. Let's okay. That's for me to understand. So
Yes.
essentially,
So essentially, what we're doing is we're taking each 8-byte segment or 8-bit segment. Sorry. All right, and we're performing the AND operation on it.
Okay.
Now, notice.
Sorry?
Yes.
Just those in game design, we haven't done any gating, any
No.
AND gates or... I mean, I understand now that they both need to be 1 in order to be true, right?
All right, so you've done programming, no? In your
Yes.
case. So you know that true and true is going to give me true.
Okay, so that's what
But
we're doing
true
here.
and false is always going to give me false, no matter whether the false comes first or whether the true comes first.
Okay.
Yes.
All right.
It's basically logic.
Makes sense.
It's logic gates, to essentially, if I'm saying, listen, for I don't know, let me
No, it's okay. All right.
for this napkin to be white, it has to be first a napkin and has to be white. Because otherwise I can't call it a white napkin. All right. If it was white and it was a piece of paper and not a napkin, then it's not a white napkin. Do you understand?
Yes.
All right. So essentially, what the important thing that I would like to sort of like point out is this AND operation. All right. Replace 1 with true, 0 with false. All right. It doesn't really matter. All right. What we're saying is that with the AND operation, both inputs have to be 1 for the output to be 1. All right. If one of the inputs, all right, happens to be 0, all right, then the output is inevitably going to be 0. Doesn't matter if it's the first one, or if it's the second one, or if it's both. Is this clear?
Yes.
All right. Now, in a very similar fashion.
So it's not just the first digit, even with the second digit is.
We're not talking about the first byte. We're also talking about the second byte, the third byte, and the fourth byte.
Yeah. All right.
All right.
Okay.
So
Okay,
notice
thank you.
that these bytes over here, all right, they're always going to be ANDed with 0, correct? In this case. Correct? And we know that anything ANDed with 0 is going to give us
0.
0. So essentially what we're doing is we are literally removing that part of the IP address, therefore giving us our network ID. So in this case, for this particular IP address, the network ID, all right? So the network ID for this IP address is 10.0.0.0. Why? Because we have taken 10.250.1.1 and we ended it with our subnet mask being 255.0.0.0. So essentially what I'm saying here is that every time you see every time you see 255 in a particular byte, all right, of subnet mask, essentially what you're going to do is you're going to be copying, all right, the byte in that particular location. Whenever you see a 0, all right, you're going to be copying the 0 from the subnet mask. Does that make sense?
I still don't know the why though. The how is okay.
The why is so that we would be able to identify which network this IP address belongs to. All right. Remember when we said we're using lookup tables and routers.
Yes.
So routers essentially is doing these IP addresses, ANDing it with the subnet mask in order to identify, all right, the network ID to see whether or not it is related to the network ID of the other devices connected to this particular router.
Okay, and where do the ISPs come in? Because the subnet mask is given to...
Yes, but this is done for every single type of network. Remember that ISPs work on level 2, class B networks.
Okay.
All right. So this is done at every level, if you know what I mean. All
Not
right.
exactly, but so a router, if it receives packets, they need to go somewhere, right?
Exactly. And in
There's an
order to
IP
identify, so essentially the router has a number of devices connected to it.
as that.
All right. Now, in order to be able to identify whether or not that packet is actually is going to a device that is connected to it, or is going to off to another router, it first and foremost needs to identify what network ID, all right, that packet needs to be in. All right. Is it going into the network that I am connected to currently, or is it going to a different network?
Which means another router. Okay.
Which needs another router, and this is why you would need to perform these subnet masks. This is obviously done at different levels. It's not just done at the router level. It's also done at the destination level. All right.
It's a method with which the packet ultimately finds its way.
Yeah, exactly. So we're using literally a bitwise operator. All right. A logic gate in order to manipulate bits. This is why it's called a bitwise operator, because we're working with individual bits. All right. In order to come up with something very interesting. All right, that's essentially we're coming up with new information.
Okay. That's
You
it.
understand that?
It's how it deciphers the packet's destination or
It-
whatever
it's-
the next step.
It identify it's how we identify the what is meant by that IP address, essentially.
Esatto.
That's all. All right.
That's it.
Okay.
So
Now-
that's all the router does under the hood.
Excuse me.
So under the hood,
Uh-huh.
it's what actually the router does.
Yes.
Its only function.
It's not its only function, no, because
the
obviously
main one.
we haven't talked about the routing tables and how it actually identifies the route, which which path it should take or snafi, and we've briefly discussed it, but essentially this is one of the steps that it actually needs to do.
All right.
All right, it's one of the steps, but this is also one of the steps that the destination computer needs to do as well. All right, or rather, the destination router needs to do as well.
Figure out that it has to accept it.
Because you have a number of different levels of router. All right, so the router that is connected with your ISP is completely different from the router that you have in your own home. You know, because of the number of connections that it has. You know, that's the main difference.
Okay, so if we zoom out, this would be identification then, sort of like an
We are identifying the network ID.
All right.
All right, whether or not this is going to be this packet is going to be passed on to this particular network or not. Okay.
I'm good. Thank you.
Mana. So essentially, this is what I was trying to get at. Essentially, when we talk about a Class A network, all right, since the number of bytes that are used in order to identify the network is only the first byte, all right, then the subnet mask for it is going to be 255.0.0.0. With Class B, all right, it's 255.255.0.0. With Class C, it's 255.255.255.0. Notice where you have 255, that is essentially where you're going to identify, all right, the network D. Does that make sense to you guys?
Yes.
Yes.
Thanks.
I have a question though.
Yes.
With this particular subnetting type,
Yes.
with this one, the one you're viewing on the slide now, there is more possibilities of IP address usage, right? With the previous one, there's a lot wasted. No?
What do you mean?
Because if you switch over to the previous slide, if you may, the IP addresses, for example, between 10.255.255 and 172.16.0.0, those IP addresses, under which class would they fall, for example?
Notice that this here, these IP addresses that we have over here, fall under Class A. All right. Why?
Yes.
Because the first byte has a value which is between 1 and 128. All right. Therefore, meaning it's Class A.
Okay.
All right. That means that this byte is going to be used for your network ID. The next 3 bytes are going to be for your host ID.
All right. So it's not specifically those numbers.
No, it's not specifically these numbers. These are the range.
Which
These are the range.
usable.
The range of usable IP addresses within this particular class for this network ID.
فهمتك. All right. My bad.
So in a very similar way, for this network ID, the IP addresses that are possible start from this network ID .0.0, all right, all the way up to that same network ID .255.255, all right.
فهمتك. All right. I understand now. Okay.
Okay.
Sorry. I was getting confused by the.
That's essentially the idea behind it. All right.
Okay.
Mala. So
Yeah, why
there
was class B a different there? Can you go on the? Because at first it's 172.16 and then it's
it's another mistake. Sorry.
31.
This should be 16. This should be 0.
Alright. Okay.
Okay.
Alright.
But
Sorry,
unfortunately,
could you just type them out? So, because there's more than one mistake in the slide now, and I'm not really sure where the mistakes are anymore. If you could just copy and paste it and fix the numbers that need fixing.
sorry.
Thank you.
That's it.
Okay, thank you.
All right. Mala.
Yeah.
Yes.
The 10.255.255. Ah, no, we did
This one here.
the first one, yes. Is that the 255? Is that the same as the subnet one?
No. I'm saying that the range of possible values for network ID starting with 10, so 10.x.x.x, x can go.
From
All
0
right.
to 55.
X can go from 0 to 255. That's it. All right. In this case, the network ID is 172.16.x.x. And again, X can go from 0 to 255. Over here, the network ID is 192.168.0, all right, .x.
Okay, thank you.
All right.
Yes, thank you.
Okay. So, right. Notice that these are the default subnet masks, all right? There are also ways and means that we can actually make use of even more subnet masks or custom subnet masks, all right? However, we're going to be seeing that in the next set of slides, all right? As I wanted to point out as well, all right, due to the high demand of Class B networks, especially from ISPs. All right, ISPs weren't all allocated a Class A address, so many of them started using Class B, and essentially, as I was sort of like explaining earlier, all right, the way that IPv4 actually prolonged its life is through the use of subnetting in order to make it easier, all right, for one to actually to reuse certain IP addresses in certain different networks, all right. But we're going to get to that in a moment, all right. I wanted to point out that the idea of subnets was first introduced by ICANN, which is the Internet Corporation of Assigned Names and Numbers, and the IP addresses assigned are assigned within subnets, such that um, ideally on the same network, all right, or the same LAN, all right, all devices connected to that IP address have similar IP addresses, all right. It is quite normal, all right, to have networks, all right, split made up of subnets, all right, in order to group different computers or different devices together, all right, and they would make use of subnet masks in order to be able to identify where the flow of traffic needs to go, all right, for certain packets. So let's take a little bit of an example. Let's say that we have an IP address of 128.184.168.0, x.x. This is essentially the network ID that we're talking about. All right. This means that all computers starting with 184 over here. This should be an 8. Sorry. So. So essentially all of the computers starting with IP address 128.184, all right, on this subnet are all going to be related to each other, all right? So the IP address 128.184.22.33 is going to be related somehow to an IP address of 128.124.55.128, for example. All right, is this clear? Because they're using the same network ID. Clear?
Yes.
All right. So here's a little bit of an example. So imagine, all right, that you're using the network ID, all right, for a particular department, all right, to be 128.192.56. All right. Notice that all of the computers in this network, all right, have similar IP addresses. The only thing that is changing, all right, is the host ID. So this has host ID 50, this has host ID 51, this has host ID 52. All right. The router here, all right, would have an IP similar to these devices, all right, but in this case on IP number 6, all right. However, it acts as a gateway, all right. So this router's IP address to these computers here happens to be this IP address over here, all right. However, this router is acting as a gateway, therefore it has a different IP address in relation to the backbone. All right. So notice its gateway IP address, all right, is more similar to the IP address, all right, provided by the backbone subnet. So the backbone subnet has 128.192.254. 128.192.254. That would be mapped into this. So essentially, when we're communicating with computers inside this subnetwork. All right. However, if we're communicating between these two devices on this subnet, we can use this IP address over here. Do you understand? This is how we can actually expand the number of IP version for IP addresses. Do you understand?
So essentially, it's like having two sides of the same.
All right.
On one side, it's saying a number. On the other side, it's saying another.
Yes, because on one side it's connected to one network, on another side it's connected to a different network.
Okay.
All right. So that is why it becomes more attainable, because essentially with every connection, what you're doing is you're then increasing the number of possible different types of connections you can actually have on Bud with the advent of subnetting. You understand?
Okay, understood.
All right. Notice that over here we have something similar as well. Over here we have a different network network ID. All right, and again, all of the devices on this network have a similar network ID but different host IDs. Okay, that is essentially how subnetting works. Okay. So, as a little bit of an exercise for you, all right, I would suggest that you would go through these different IP addresses in order to identify the class, all right, using the table that I had provided with you at the beginning of these sets of slides, all right. Oops. And for these over here, I would like to identify the network portion, all right, and the host portion of these IP addresses. Essentially, it's taking what we have just done over here. So identify which part is the network ID, which part is the host ID. Okay.
Could we get the answers to this? I mean, if we do this at home, this exercise, I would like to know if I got this right or not.
Essentially, it's very straightforward. If you take one of these, all right. So let's take this first one as an example. So 177.100. So I'm only going to look at 177. So if you take a look at this, 177 falls under class B. All right. Therefore, so let's actually make it a bit easier. Control Shift. Windows Shift S actually. Whoops. So if I take this, and I take this, so in this case, first number 177 falls between 128 and 191. Therefore, this is your host ID, your network ID. This is your host ID. All right. 119. All right. 119 falls between 1 and 126. So this is your network ID. All right. This is your host ID. It's pretty straightforward, as in this one over here, 209. 209 falls in class C. So this part here is your network ID. This part here is your host ID. All right. 119. All right. That's part C as well. Our class C. So that is your network ID. This is your host ID. All right. Notice I'm
ġifiri, the network ID, for example, the first one is 177.100.0.0. If it has to be like the network ID of that particular.
what Erja?
The first one.
This one?
So the network ID is 177.100.0.0 in that case. The network ID.
As that.
That's what you were trying to explain with the
Yes. All right. So notice the way that I am identifying which class it is in. I'm looking at the first number. All right. I'm identifying it whether it's class A, class B, or class C, depending on these ranges that I have over here. 117 is in the first class, so it's class A. So that is your network ID. That's your host ID. You know, essentially that's all I'm doing. I don't know if that is okay for you,
Yeah.
Bridget.
Yeah.
Yes, it's clear. Thank you.
Okay.
Sir, I'm not sure if this was mentioned before, but the first class A, first
Yes.
byte, the range is supposed to be 1 to 1 to 7 or
No. It's 1 to 1 to 1 to 6 because
1 to 6.
Because 1 to 7 is actually used for something specific, but
for local something وش.
It's a special kind of.
No worries, no worries. You don't have to explain. Taser, scusani, I don't want to waste
No,
time.
no, no. These are correct. These I know they're correct.
Alright,
Okay.
alright. Because I just saw that 1 to 7 was missing and I was wondering. No.
I know. That is because the 1 to 7. All right. If the first byte is 1 to 7, it's used for a specific purpose. As I said, these are generic cases essentially.
Thank you,
Okay.
sir.
All right.
Will we need to know these ranges for the exam? What's A, B, C, D, and E?
A, B, and C definitely. D
Okay.
and D are good to know. But yes, knowing the different classes and the ranges for the first byte, at least, those are important to know. Yes.
Okay, thank you.
Okay. So yes. Which part? Sorry. Yes. So essentially, the gateway allows you to go from one network to another network. In this case, all right, Mala, subnetting, all right, what we were doing here, all right, these are default subnet masks, all right. You can have what are known as custom subnet masks, all right. So in this case, all right, even though that 128 here, all right, basically means that we are a class B network, all right, it could be the case, and in fact it is, that we are only using the last byte for hosts, all right. So in this case, the subnet mask for department A's network would be 255.255.255.0. It would be a custom one, all right. The same thing would apply to this one over here, all right. It will have a similar subnet mask. Notice it's a different network ID, but it's a similar subnet mask, all right, and as well as the backbone, all right. The idea behind the gateway is that essentially, when you have a device that is spanning multiple networks, it can have an IP address on one side and another IP address on the other side. All right, depending on which network it is facing, essentially. All right, does that make sense? All right. Any other questions, guys? All right. So that is essentially that portion that we had for the IP addresses and subnetting. I just wanted to also mention this idea of yes, Mana, guys, this set of slides, all right. So slide number 13 basically talks about the difference between ICMP and DHCP. Essentially, it's the idea of how you can control messages on the TCP/IP network, as well as the dynamic host configuration. This is essentially how we can actually assign IP addresses to computers that are joining a network in this case. I would like you to read through this in order to understand what is going on, all right, within them. Essentially, what these set of slides does is it explains, all right, how these two different sets of protocols actually work. All right. As you can see with the ICMP notifications, you have ping, you have trace route, which you should be aware of with regards to your assignment. All right. Redirect message. You have a number of different other forms of services that are provided by the ICMP protocol. All right. So I would like you to please take a look at this these set of slides, because I would really like to cover the last set of slides over here before we call it a day. I'm sorry that we're going way beyond the amount of time, but I feel that it's very important that we actually cover this together. Okay.
Jeff,
Yes.
it's a very quick question. In terms of the exam,
Yes.
all the 14 chapters are a priority, or, for example, if you say the last two chapters
No,
are
the chapter before this one was not that much of a priority. This one is going to be more of a priority. That's why I want to cover this before we end today. Okay. That's why it's important that we talk about this one. All right. It basically follows on the last chapter that we were talking about, which was subnetting essentially. Okay.
Firkas, before we close off, can you not give us a hint or anything? It's not that, but maybe assist us in prioritizing which chapters are heavier in terms of.
The last chapter that we just discussed, the idea of classes and subnetting, that is going to be important. This is going to be important as well. The layered architecture is going to be very important as well. The TCP/IP headers is going to be quite important as well. And these were. This is basically what happens when a link is clicked. And classifications, these are also going to be important for you to understand. So topologies, scale, connection methods, typo, those are going to be important as well. All right. Excuse me. The exam is going to be quite straightforward. It's going to be, if I'm not mistaken, 6 questions. And you have to do all of them. Let me just double check very quickly. So, show preview pane. Essentially, it is. It's a 2-hour question. It's a 2-hour exam. You have 5 questions. All right. Essentially, you have elements such as fill in the blanks. To type questions. You have true or false questions, explaining where you have false false statements. You also have for example, description. So what is the difference between this kind of topology versus another? All right. What is the difference between these different types of IP addresses? All right. What class do they belong to? You know, those kind of questions. Okay.
I don't know if share screen is not switched on at the moment. I don't know.
I'm not sharing the type of. I'm not sharing the exam paper.
Where's the try?
I'm not. I might be tired. I'm not that. I'm not that silly. You have 5 questions to do in 2 hours. All right. You have true or false questions. Fill in the blanks. Yeah, you have some description questions. You have some questions where you have to do work out IP addresses and so on and so forth. All right, that kind of stuff.
Okay.
All right. Remember that this is not worth as much as your final exam, because we also have the final exam. Okay, which is worth more. All right, and then we'll also have some time in order to do some revision, so we'll be able to cover certain elements a bit more leisurely as well, and a bit more in detail. Okay.
Fair enough. Fair enough. No,
Right.
if I'm, let's put it like that. Vera, this is more of a test rather than a final exam, but I want to keep my my average.
Oh,
So
I understand that. I understand that, and I also understand that the amount of stuff that we need to cover in a part-time session is also restricted with time. So
sometimes it borders on a bit on the too much level.
it could be,
Yeah,
yes,
completely.
yes. I have had that argument placed to me in the past, and I have made that argument on your behalf in the past as well. So don't don't worry, I've said that as well. All right, I'm on your side.
Thank you.
But I'm trying to. I want to make sure that you're prepared for the exam. You know, at the end of the day, you know. So I need to we finish off these last set of 18 slides, and then we'll call it a day. All right.
Yes, sir.
Okay. So in this set of slides, we're going to be looking at the how a TCP connection is actually established and how flow control is actually managed within TCP IP connection. Essentially, if you remember, we talked a little bit about the TCP IP header, which, as we said, is made up of a number of different segments: the source port, destination port segment, etc., etc., etc. We're going to be focusing primarily a little bit on these flags, as well as the sequence number and the acknowledgement number, in order to understand how a TCP connection is established in the first place. All right. So essentially, whenever we want a reliable connection, a TCP connection is created. All right. And it's essentially based upon the idea of a positive acknowledgement with retransmission. What does that mean? It means that every time a packet is received, the receiver will send an acknowledgement packet back to the sender to tell it that it has actually received that packet. And this is done through the use of the acknowledgement flag, all right, by setting it to 1, all right. If the receiver does not receive that acknowledgement packet within a set given amount of time, then it is automatically assumed that the receiver did not receive that packet. All right, even if, for instance, the packet, all right, of acknowledgement is received later. All right, it will, after a certain amount of time, it will assume that the receiver hasn't received the packet, and it will resend it. It's kind of like what we would all imagine or we would hope Amazon would work like every time we order a packet. All right, every time we didn't receive a packet, it would resend it again. That's what happens at TCP. It doesn't happen with Amazon. I'll argue with Jeff Bezos with that. Okay. So essentially, there are a number of different reasons why a packet might not arrive. Okay. So it might be the case that the sender might not receive an acknowledgement for the simple reason that the packet was lost or got corrupted in transmission, or the packet was delayed and received later. So we have a delayed delivery. It might be the case that the acknowledgement packet, on the other hand, was lost and corrupted. It could be that the acknowledgement packet that was sent back was also delayed. So there are a number of different reasons as to why the sender might not receive back the acknowledgement packet in a given amount of time. So essentially, there is this timeout function, all right, that when that timeout expires, it automatically assumes that it needs to resend that package back to the receiver. Obviously, it's not that much of a problem for the receiver, because if the receiver is receiving multiple duplicate packets, it would know that one packet is duplicated, in which case it will literally ignore it. All right. So essentially, receiving duplicate packets from the receiver's end is the receiver's problem in that case. All right. But all of this is actually happening within the transport layer. Okay. So what is actually happening whenever we're trying to set up a connection? So let's say that device A wants to communicate with device B. So device A sends a message, all right, to device B, and he receives the message. Ideally, device B would send an acknowledgement back saying that it has received it. All right. Let's say since it has received it, therefore it doesn't need to resend that particular message. Let's say that now it wants to send another part of that message. So it sends that message, and let's say that somewhere across the line, that message was lost. It was corrupted, or it collided with something, or something of the sort. All right. So that message has not arrived. Therefore, B hasn't received the message, therefore hasn't sent an acknowledgement back. After some amount of time, the timer has expired, and you would resend the message, all right, and hopefully you would receive an acknowledgement back. That is essentially the idea behind the acknowledgement system. Okay, so that is essentially what is going on within TCP connections. However, everything that is happening within a TCP connection is going to work in this way after, first and foremost, you establish a connection between these two devices that are actually communicating with each other. The establishment of the connection is known as the three-way handshake. And guys, take the hint. This is very, 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 very important. Okay? Take the hint. All right. I might have not shown you the exam paper, but right. So what goes on with the three-way handshake? Let's say that client A wants to establish a connection with server B. All right. So A contacts B to check whether or not a route between A and B exists. And once that is established and B accepts the connection, it will send an acknowledgement back to A, all right, based upon A's request. Once A receives that acknowledgement, then A will inform B, all right, so client A will inform server B, all right, the starting sequence of the number of data packets that it's actually going to be sending. all right? So that would allow, all right, the server to identify whether a connection is a new one or an old one. So essentially, for every connection that has been established, you would provide it with a different sequence number. All right. So the sequence number is essentially the number that you're going to do, that you're going to use as the start of your sequence of packets that you're about to send. Is this clear so far, guys?
Yes, it's clear from my end.
Okay. So what is really going on underneath? So let's say client A wants to initiate a connection with B. So A sends a signal, all right, or sends a packet to B with the sync flag set to on, all right. So that is essentially the first step, all right. The segment, all right, would inform B that A would like to start a communication with B, essentially having having the sync bit on, all right, and the segment value, all right. It informs B that A wants to communicate with B, all right. B then, all right, takes the sequence number, all right, that has been sent by A and starts its segment with it, all right. So essentially, B will it informs B, all right, what sequence number is going to be used by A when it's going to start sending numbers to it, all right, or sending data to B, all right. And this, again, this sequence number is going to be new, all right, for each connection that A is going to make with B, just in case the connection expires or something of the sort, or you don't want to have a previous a communication tainted with a previous connection, all right, for some reason or another, all right. So therefore, every new connection is going to start with a new sequence number, okay. On the second step, all right, so B is going to respond to A by sending both the sync flag and the acknowledgement flag on, all right. And it's going to also reply, all right, with the acknowledgement segment, all right, in the acknowledgement segment of B's packet, including A's synchronization segment. So essentially, if you remember, we have a sequence number, all right, and an acknowledgement number. So when A is trying to communicate with B, is going to set forward a sequence number, all right, and the sync flag being on, all right. B is going to return a packet with the sync flag on and the acknowledgement flag on, and the acknowledgement number being the sequence number, all right, that was provided by A. Essentially showing A that we are establishing a connection based upon the sequence number. Does that make sense, guys?
It's like confirming the sequence number, basically.
Excuse me?
It's like confirming the sequence number back to A, basically.
Exactly. All right.
Okay.
And it's also providing, all right, it's also providing the sequence number that it will start with. So notice B is going to have a sequence number for itself, all right, which is going to obviously be sent on the sequence number element from B side, okay. But this number that was provided to it by A is going to be returned back via the acknowledgement number, essentially. Okay?
Okay.
So that's the first step. And the third step is essentially A will acknowledge B's initial sequence and send back the acknowledged signal. And therefore data starts to transfer. So if we had to look at this in a more diagrammatic approach, all right? So we have participant A trying to communicate with server B, all right? It sets the sync flag on, and it sets a sequence number being X, all right? The receiver will send the sequence number, all right? And the the sequence flag and the acknowledgement flag. It will send its own sequence number Y, and it will provide an acknowledgement being the sequence number provided by A plus 1. All right? Essentially meaning that it has received that particular sequence number. A will then resend back another acknowledgement, all right? This time around, taking the sequence number Y, all right, as its acknowledgement number plus 1, all right? And that there is your three-way handshake. Is this clear, guys?
Yes.
The handshake is clear. So this happens before
This happens
communication starts.
This happens at the start in order to establish communication.
All right.
All
Clear.
right.
Thank you.
Okay.
Yes, that's clear. Thank you.
All right. So this is again step-by-step sequence. So sync number, synchronization flag is set to 1, meaning that you want to establish a connection between A and B. And the acknowledgement flag is set to 0, and you have your sequence number, all right, which is A's initial sequence number, all right, which is essentially the first byte transmitted by B would be the sequence number sent by A plus 1. All right, B receives the packet, all right, and sends back an acknowledgement, all right. So it's sending a sync with the sync and the acknowledgement flag, setting them both to 1, setting B's own initial sequence number and transmitting an acknowledgement number being the A's initial sequence number plus 1. All right. When A receives B's acknowledgement packet, then it will set the sync flag to be equal to 0, the acknowledgement flag to be equal to 1, sets its sequence number to be a initial sequence number plus 1, and B's acknowledgement number, A's acknowledgement number being B's initial sequence plus 1, essentially. And therefore, you would have established your three-way handshake. If you would like to see this explained in a slightly different fashion, all right, you have this video over here, which will also explain it to you. I would highly suggest that you do that, all right? Now, the last thing that I would like to talk about is the idea of flow control. So essentially TCP/IP uses, or TCP rather, uses what is known as a sliding window for flow control, for a flow control protocol. Essentially, each segment, all right, in each segment, the receiver is going to specify, all right, the amount of additional received data that it is willing to buffer in the collection. Essentially, when you're sending data across, it is very inefficient to read data a packet at a time. All right. Ideally, what you would do in order to also make best use of your system is to buffer your data. So you would collect an amount of data, all right, and read that amount of data at once rather than having small bits being read individually. Also, all right, it helps with with devices which are slower, which might act slower than others. Essentially, you might have a host, all right, where it's running slower than another host, all right, that is trying to send to it, and in order to not overflow it with the amount of packets that you are trying to send it, and therefore maybe possibly crashing it, all right, TCP uses what is known as flow control in order to limit the amount of data that it might be receiving at any given point in time. Essentially, you make use of a window, all right, to identify how much data that host is expect or can actually receive. Essentially, it is going to be acknowledging the amount of space left within the buffer, all right, that each host is actually going to have, all right. So essentially, all right, what you're doing is, let's say that this is um, uh, your sender, all right, and this is your receiver, all right. So this is the sender. So the sender wants to send this data, all right, in this particular order. So it's sending frame 0, all right. It sent frame 0. It hasn't received an acknowledgement yet, mind you. All right. So it says, okay, I've sent frame 0. I'm going to set frame 1. So it sends frame 1. All right. In that case, all right, and once it sends frame 1, let's say that our receiver has actually received our first frame. So it sends back an acknowledgement that it's received frame 1. In which case you say, all right, I can now shift, all right, my window. Notice the window by 1. So notice it has received frame 0. So I'm going to shift this by 1. So notice it's going to shift the window every time it receives back an acknowledgement. All right. If it doesn't receive these acknowledgements, it won't shift the frame. Therefore, it won't flood the receiver, all right, with packets that it cannot actually handle. Does this make sense to you guys?
Yes, but it seems to have a predetermined limit now because the window goes up.
Yes. In fact, you would, if we had to take a look here, that's our window size. So essentially, when you're setting up your TCP IP connection, you're actually going to determine what your window size is actually going to be. All right.
Yep.
That's so you're getting to understand what this actually means now.
So in this case, the window size is just 16 bits, correct?
It's going to tell you the number of bytes. Sorry, I'm trying to find. It's going to tell you the number of bytes, all right, that the sender or the receiver can actually handle. Okay.
Deep dive into this later.
Huh?
I'll deep dive into this a bit later.
So, imagine, essentially what we're saying. Imagine every frame is 1 byte. All right, to keep it simple. All right. Then in this case, upon the establishment of the three-way handshake, you're going to have in the window you'd have 1, 2, 3, 4, 5, 6, 7. You have 7 bytes. So the window size would be 7 in this case.
Okay. All right. So it shifts. It shifts only in one direction from left to right.
No, it's you're sending these in order. Notice you're sending frame 0, frame 1, frame 2, frame 3, frame 4, which are the order that they're in over here. But you're only going to shift the window from the sender's point of view, all right, every time it receives back an acknowledgement, all right, and you're also going to shift the window for the receiver every time you sent the acknowledgement. Once you know you've sent the acknowledgement, then you shift the window because you now know that the rest is actually going to be data that you're going to be processing.
Alright, so the rest, for example, where there is frame 0, it received only a 0 and that's it. No acknowledgement was sent back, Malat stays where it is.
Exactly. So once it received the acknowledgement notice, it moved forward.
Okay.
Right? The idea is so that you don't flood either sender or receiver. That's the idea.
Alright. Thank you, sir. Thank you.
Okay? That's essentially it, guys. All right. Thank you very, very, very much for listening. Thank you very much for your patience. I'm sorry I've taken so much out of your time. All right. I would really like and hope you have you do well within your exams, obviously. If you have any questions between now and obviously your exams, feel free to message me. I will try to answer you as quickly as possible. All right, so that you'd be ready to confront your examinations. So,
Thank you, sir. Thank you for the extra time. Thank you.
thank you.
Thank you.
Good
We'll see you
night.
next week.
Yes.
Thank you.
Ciao, ciao. Bye bye.
Thanks, Jojo.
Thank you.